That gives me more material to put on the test. Okay, so last time we were talking about IP. We said that there were three types. What are they?
First party, second party, third party.
First, second, and third party. And first party is the stuff that you write. Second party is what the FPGA vendor, the manufacturer of the FPGA chip, will provide you. And the third type is produced by companies that don't manufacture FPGAs, they do manufacture IP, and they coordinate with the FPGA vendors to make sure that the IP they have written works efficiently and it's got good timing, etc., on their particular FPGAs. The second party IP that we looked at last time was pretty basic. For Xilinx, we had some memory primitives, which gave you simple memory devices, and you'd have to construct a wrapper to connect these primitives together to form larger memory chips. And then we looked at, I think it was a binary counter. It was pretty sophisticated, but still a binary counter is a pretty basic circuit. To give you an idea of how sophisticated some of this is, Lattice Semiconductor has a 1553 encoder-decoder, and this is for the mill standard 1553 low-speed serial bus used in avionics systems. And if you look at the block diagrams of these for the encoder and decoder, it's a pretty sophisticated device. In the encoder, you have a serializer, something called a Manchester encoder, a MUX, a bit counter, and a parity generator. And on the decoder, you have a transition finder, a sync pattern detect circuit, a bit counter deserializer, and a parity check. And of course, they have complete timing diagrams and so forth. I did want to show you on this particular data sheet the type of files that you will get when you get IP, either second party or third party. See that you get a whole bunch of different types of design files, Verilog source files. They have files that can be used for placement and routing and so forth. Got a couple of examples to show third-party IP. This is from a company called Art Silicon. And in this particular case, they're talking about a JPEG decoder encoder. So the data sheet gives you the features, a description. Something I found particularly useful is they show you for various Lattice FPGAs the frequency that you can expect this thing to operate at, and it tells you how many slices, block RAM, and DSP blocks are going to be required to actually implement this JPEG encoder decoder. What's block RAM?
This special type of block in the FPGA specifically uses RAM rather than having it distributed throughout.
Say it in one sentence. Somebody else. What's block RAM?
It's RAM that's set aside on the FPGA.
It's what?
It's just RAM that's set aside on the FPGA to be used as RAM.
Simpler.
It's RAM?
It's hard IP. As opposed to distributed RAM, where you're building up a RAM using LUTs out of the FPGA fabric. Block RAM is hard IP. It's a memory chip in every sense of the word, separate from the FPGA fabric. You have to instantiate it, but that's what they mean by block RAM. You got to make sure that you understand the concept of distributed RAM and block RAM, because it comes up over and over and over and over again. I want to show you a couple devices that are made by Synopsys. This is part of their Designware family of IP that they provide. So I have some examples in here. Well, you can't get a much simpler block than this. This is a decoder. Like a 74-138 3 to 8 line decoder. So you have an input A and an output B, and there's your block diagram. The A input has so many bits in, it's binary encoded input data, and it has 2 to the width outputs, which are decoded output data. This is doing a binary to decimal conversion for you. So if I have 4 inputs, I've got 16 outputs. This uses a parameterized word length, so it's followed that good design practice of using the module instance parameter override when they coded up the module. So they give you both VHDL and Verilog simulation code. The simulation code is different from the Verilog source files. The simulation code is just a Verilog or VHDL module, but it doesn't have all of the particulars of how it was actually implemented with case statements or continuous assignment statements or whatever. It's just a simple device that can be used for, or module that can be used for simulation purposes only. When you are going to use this in your design, you have to use the actual Verilog source code module, not the simulation file. They just did this so that it's efficient to simulate and will improve the turnaround time for your simulator. So they give you an example here of what you can expect. In this case, I've got a width of 3, so I've got 8 outputs, and you'll notice that the way this is set up, the asserted output is always a logic 1, and all of the rest of the outputs are a logic 0. Continuing on, they show you example code of how you would infer this. Stanley, I'm not sure if I covered this before. Difference between inference and instantiation. Have I discussed that before? Well, seeing as we've got this word here, function inferencing, let me do a sidebar. This is a very, very, very important concept. Not only will it be testable, but it's something that you need to know if you're actually going to use FPGAs once you leave Portland State. Instantiation, you know, is the process of creating an explicit object in a design. So I've got a module I've written for, I don't know, let's say a parity checker. And in my design, I specifically instantiate my design into my final design. Whatever the module name was, it's specifically called out, the ports are connected and so on in the module I'm instantiating it. That's instantiation. Inference. If you are inferring something, what you're doing is you've coded up your description in such a way that it makes a suggestion to the synthesizer on how to implement the circuit, but you're not telling it exactly how you want it implemented using specific hardware devices. Let me give you an example. We discussed this before. If I write that code in my Verilog description, what does that get synthesized as? We discussed that when we looked at different syntax and the types of devices that would get synthesized.
Mux.
A what?
Mux.
A mux. If I write an if then else statement, I am inferring that the synthesizer used a multiplexer to implement. Here, I told the multiplexer specifically what I want, and I've got a module template called mux underbar 2 underbar 1 with an associated port list. And that's specifically what I want put into the design. So in an instantiation, you tell the synthesizer, synthesizer's not free to do whatever it wants to, you've told it exactly what you wanted. Inference, you suggest by the way you've written your code on how the synthesizer might implement it, and the synthesizer will figure out the final implementation. Okay? So that's the difference between instantiation and inference. So back to my designware component. They show you sample syntax here that you can use. Let's suppose that I want to use this decoder, but I want to call it as a function. So in here, I'm going to declare an input func A, and that's the width, the output, and notice how they define the output here. 1 left shifted by func width minus 1. That's the most significant bit. And they have a parameter statement up here which tells you what the func width is. Then down here I have a continuous assignment statement. There's the function call, and there's the parameter the function requires. So if you wanted to use a function call for this particular designware component, that's the syntax. They also show you how you would instantiate. Again, parameter width will tell me how many bits wide it is. I've declared my inputs and outputs. There's the module name. Notice the parameter override. Circuit reference designation, connection by name. So they show you the syntax to instantiate it. Next device is a parity generator used for checking the integrity of data that's being transmitted between two places. So it takes data in and then generates a parity output. So you have data coming in of a certain width in terms of number of bits, which can be as high as 256 bits of data. And you also have a parameter 0 or 1 that defines whether you want even or odd parity. So in the data sheet, they tell you if you have even or odd parity, what the parity type parameter should be. Function inference is obsolete. So they tell you don't use function inference if you want to use the parity generator. So you have to instantiate it. And there's the module name, parameter overrides of width, and the parity type, connection by name. The last one, and I thought this was kind of a clever device, the min-max. You have a variety of inputs and two outputs called value and index. The number of bits in the input is number of inputs times the width of each input. What I'm going to do is I'm going to input a vector. And what this device is supposed to do is tell me the maximum value in the vector and tell me its index number. Or you could do minimum. Tell me the minimum value in the vector and tell me its index. So here are the inputs, the min-max input here. You define whether you're looking for the minimum or the maximum. You do have 2's complement control. And it will output the maximum component in the vector and its index. So here is a simple example to illustrate how this works. Let's suppose I have a vector that's got 4 components in it, index 0, 1, 2, and 3. And each one is 6 bits wide. So the total input will be 4 times 6, or 24 bits. So you apply this in, and it's going to take, let's say I set this up for maximum. If A2 is the maximum component in this vector, A2 will appear on the output lines, whatever that value was, and the index 2 will appear on this output. This is kind of a nice device. It would be a great homework problem. Design and simulate a module type. Okay, that's the issue. Here's function inference. So there's my declarations. And down here, I have a continuous assignment statement. It's an if, then else statement. The TC determines whether or not you want 2's complement representation of the numbers or not. And if it's maximum, you'll output this, otherwise you'll output that. Either minimum unsigned or signed, or maximum unsigned or signed. So they do it with a nested if-then-else statement. The instantiation is considerably easier. There's your module name, module parameter overrides, connection by name. Incidentally, touching back a moment on this inference versus instantiation, one of the things that we said in writing these Verilog modules, and one of the reasons why you specifically use the module instance parameter override, is for reusability. You designed something 6 months ago, I want to use it in my design. I can take your code and drop it into my design with possibly no modifications whatsoever. If you use that module parameter instance override, when I instantiate your design, I just had to specify which parameters I want. So your code is portable. I can use it in my design without any modification. Let's suppose I've got a design that's working on a lattice semiconductor FPGA. And my company has decided, well, we're going to start using Actel FPGAs. So I need to port the design that was running on the lattice semiconductor FPGAs onto an Actel FPGA. Which is going to be easier? Code that relied on inference or code that relied on instantiation?
Code that relied on inference.
What?
Code that relied on inference.
Why?
Because you're hinting the synthesizer instead of like explicitly like instantiating that module. Instead of like directly calling a module that is on it. And you don't know how that module was implemented.
Well, it's a little more involved than that. If all of the code in the design was first-party IP, probably wouldn't make a difference. But what if you use second-party IP? Specifically, you instantiated some library component that Lattice gave you. And what happens if Actel doesn't have that component? Your code is going to have to be rewritten. Third-party IP. Maybe the third-party IP works on Xilinx and Lattice semiconductor FPGAs, but not Actel. What do? You may have to switch to some other third-party IP vendor to get the code. The code will be more portable if you rely on inference rather than instantiation. That's the advantage of inference. What's the advantage of instantiation then?
You get exactly what you want.
You get exactly what you want. You get control. You told the synthesizer precisely what modules you want implemented and how they're to be implemented. So it's a trade-off between portability and control. And whichever is more important to you will dictate whether you decide to infer designs or instantiate the designs. Okay, the next topic. We talked about the FPGA vendor giving you a library of components, second-party IP, as an inducement to use their particular FPGA. You don't have to do so much coding because they're going to provide you with commonly used digital designs. One thing else that the FPGA vendor will do is they will provide you guidelines on how to write your code so that it can be efficiently implemented on their FPGAs. Now I'm going to show you a document here, and then we're going to look at a couple of videos that Silence put together. But I want to go through the HDL synthesis coding guidelines for Lattice FPGAs. So as it says here, coding style plays an important role in utilizing FPGA resources. Synthesis tools are quite sophisticated. However, it is still the responsibility of the user, that's you, to generate meaningful and efficient HDL code to guide their synthesis tools. Syntax does matter. So this application note is going to talk about things like hierarchical coding, design partitioning, coding styles for finite state machines, using pipelines, comparing if statements with case statements. If statements and case statements semantically are identical. However, in some circumstances, it's more efficient in terms of resources used if you use an if-then-else rather than a case statement. Now, this document, and every FPGA vendor will provide you with this type of information. Those of you who are wise will read these documents before you write your first line of code. Remember my first law, design before coding. This is part of the design. Find out, you're going to know what target FPGA you're going to use. Find out what that manufacturer recommends you do when you write your code, because it'll be more efficiently implemented on their FPGAs. And as we will find out, different vendors make different recommendations. And some of those, when we get to the Vertex 5 coding video, has a surprising requirement on writing code. Okay. Since designs in smaller blocks are easier to keep track of, it is preferred to apply hierarchical structure to large and complex designs rather than having one monolithic module. We talked about constructing the design hierarchy when we were talking about managing complexity. Since the top module should only contain instantiation statements. Any I/O instantiation should be at the top level of your hierarchy. And any signals going into or out of devices should be declared as input, output, or bidirectional ports at the top level. And memory blocks should be kept separate from other code. So if you're going to infer a memory, that should be in a completely separate module, not buried in some other module. Maintain synchronous sublocks by registering all outputs. Registered outputs are suggested to arrange the design boundary, to consider the implementation of the combination of logic and registers into the same logic block. Registered outputs makes the application of timing constraints easier. We're going to be talking in a future lecture about timing constraints. It makes it easier to analyze the timing. It makes it easier for the synthesizer to satisfy your timing constraints if you have registered the module outputs. So for those of you who don't know what a registered output means, they show you in this simple block where these are 3 modules. This block is just combinational logic. This block just has a register. Let's merge these two, and now I have a registered output on this module. And this module has a registered output. Next guideline. Keep related logic and shareable resources in the same block. This allows sharing of common combinatorial terms. So they show a design here where I've got some logic driving a register. This comes into a multiplexer and some more combinational logic, another multiplexer and a register, and it's recoded to look like this. Separate logic with different optimization goals. In some cases, you may want to optimize a circuit for speed. In other cases, you may want to optimize it for area. How much space is going to be required on the silicon to implement it. If I have different combinational blocks, one is supposed to be optimized for speed, the other for area, don't put those in the same block. It makes it more difficult for the synthesizer to meet your optimization goals if they're in the same block.